let's talk briefly about three things: symbol tables, string tables, and the data in your program. And we'll pick on the last one first. The data in your program is just your program's data. It has whatever meaning your program assigns it. So for a little program like my little fancy Hello World program, the data is pretty simple. It's just some strings. And so I can take a look at that using, let's say, objdump. So I can say I want just the data section. And we can say I want to see the data. And there it is. And it looks like a string table in a way. It's a bunch of characters, or it can be interpreted that way. But again, these are just some bytes. As far as the loader and the operating system know, it's just bytes. And they're not even null terminated strings. They're just strings of bytes. And that's it. All right. Let's go over here and let's actually begin to take a look at what's in hello. So let's just do a quick dump of hello and see what's there. So this says, hey, there are two interesting sections. There are more sections than just these two, but here are some interesting ones. There's a text section that contains a program, and there's a data section that we've already looked at that contains some data. Let's see what the sections are. And we'll use elf for that, or read elf for that. So here are the sections, and now instead of just seeing those two, I see several. I see a null up here. Then I see .text, .data, .symtab, .strtab, and .shstrtab. And it tells me, hey, these are program bits. I don't know what they are. It's something to do with the program. The interpretation is up to the program itself. Same thing for data. But these have a different type. This is a symbol table, and these two are string tables. We can take a look at what's in them using XXD. So let's go ahead and do that. Let's go ahead and take a look at what's in strtab and what's in shstrtab. So we can't look at it using objdump like we could the others. Because objdump doesn't know about it. It's just the way that program works. But we can use XXD. I'm going to do that to say group by single bytes. And you can tell it where to start. So where does, let's say, .strtab start? Well, this tells us it starts at 21D8 in hex. How long is it? Well, this tells us it's 7A in hex in length. And there it is. This is the content of this string table right here. .strtab, which is a string table. Here are the bytes that make it up. And it's full of null terminated strings. Pro forma, it begins with a null and ends with a null. If you look at the man page for ELF, it'll tell you that it has to do that. So we can think of this in two ways. We can think of this as an empty string that begins it, or we can just think of it as a leading null. Here is the first actual string that's present in this string table. And it's HELLO period ASM null terminator. These are null terminated strings. So at offset 1, I have the first string. That's followed by an underscore STAR T period TARGET 2 null termination. Okay, so there you have it. That's the string right there. And it goes on like that. Great. What's in the other string table? Because there's this sh stir tab. Let's take a look at it. It is at position 2252 into the file. And it is hex 27 bytes long. And these are, again, I'm using XXD. XXD just knows there's a file with some bytes. And this is the offset into that file. Just go to that, count that many bytes into the file, and then dump out this many bytes from that location. And here they are. Another symbol table begins with a null, ends with a null, it's required. And then we have period, SYMTAB null, period, STRTAB null, period, SHSTRTAB null, period, TEXT null, period, DATA null. These are the names of the sections. Wow, okay. So this is a string table associated with the section header table. What's in that symbol table? Let's go take a look at it. Right here it is. And we see it begins at location 2040 and it continues for hex 198. So let's go up here and make that offset 2040, make that 198, and see what we get. And we get this. So this is the symbol table. It's a whole bunch of bytes. And what in the heck is going on in here? Well, one thing we notice is I don't see any symbol names. It's okay. The symbol names are up in here. Okay. So what I'll expect to see in here are pointers in some form to entries in here. How is this laid out? To find out, we can look at the man page for ELF. So here we are in the man page for ELF. We go down to the string and symbol tables, and sure enough, here is an entry for the symbol table on a 64-bit system, and it consists of a 4-byte offset to the name. So what is that? I can look down here and it says this member holds an index into the object file's symbol string table, which holds character representations of the symbol names. If the value is non-zero, it represents a string table index that gives the symbol name. So we can never use the offset 0. And so it's fine to put a null there. So now we understand a little more about that. And so we would expect the first string to have offset 1 and so on. So this is just going to be it's not a pointer because it's not 64 bits. It's just an offset into that table. And that's the first 4 bytes. That's followed by, oops, I'm looking at the wrong one. That's followed by a single byte which has some info, another byte which is some other info, and then this guy, a 2-byte section header index. We'll see what that is in a few moments. Then there is this 64-bit value and a 64-bit size. All right, enough of that. Let's go take a look at the actual symbol table. And let's do it in 2 different ways. Let's use ObjJump over here. There's the symbol table. And let's use readelf over here. And there's the symbol table. They're displaying the same things, but they're going to display them a little differently. And maybe we can learn something by looking at both of them and going back and looking a little bit at the definition. So both of these are tables that map symbolic names over here in the far right column to values, which happen to be over here in the far left column. readelf is helpful enough to provide some header names for the columns. So over here is the name, and over here is the value. Several things to notice. readelf gives us this row, which is 0, no type, undefined. Objdump omits it. readelf doesn't give us any names for these two, but objdump tells us, hey, they're .text and .data. We'll see a little more about why that happens, but basically, you remember there was a case where it said if the offset for the name is not 0, then it tells us where to find the symbol. Well, it turns out the offsets here in these two entries are 0. And so you can look right here. This is the section index. Let me go back. This is this little guy right here. Okay, this is STSHNDX. Let's go down and take a look at that. Oh, it's pretty far down. There it is. Every symbol table entry is defined in relation to some section. This member holds the relevant section, header, table, index. Or it doesn't correspond to any section. And if it does, we get this. ABS. It's an absolute. In this case, this is an absolute value, like right here. Here's a symbol, stir1.len. This is the length of string 1 in my program, and it is hex 16 bytes. So that's 16 plus 6, which is 22. It's 22 bytes long. Here's a string, and it occurs in section 2. Now over here, objdump has actually decoded that for us and tells us that that's data. So in a section 2 is data. Here's the symbol that starts in section 1. Here's that same symbol. It's in text.text. So section 1 is text, 2 is data, and so we can now interpret this up here as text and data, which is in fact what objdump does for us. All right, what are the values? Well, we already saw one value for the length, which was just the actual value itself. String 1, however, we want that to be the virtual address of string 1, and there it is. There's the virtual address of string 2, there's the virtual address of string 3, etc. Okay. And that makes sense. String 1 is the first string. It would be at the start of the data section. This is where the data section begins. This is the virtual address for the beginning of the data section. All right. More we could talk about in here, but other than pointing out that these are both type section, which is how it knows to interpret them as section names, there's not really much else to talk about here. We know that each entry is 4 plus 1 is 5, 6, 7, 8, 16, 24 bytes long. 24 in hex is 18. If we take a moment and remember this, we'll see that here is the symbol table, and this entry right here corresponds to the entry size, and sure enough, it's 18. So we know that each entry into the symbol table is 18 bytes long. Now, the symbol table begins at 2040. And we know it is 18. And this is a hex number, so I need to put a 0x in front of it. And so this will be the 0th entry. And it's all zeros. And that corresponds to this one right up here. It's not listed in the objdump table, but it is over here in the readelf table. Let's go ahead to the next entry. We'd add hex 18 to hex 40, and we get hex 58. And it's just 18 in length again. And there it is. And so now, let's break it up into those pieces we saw. We know that the first 4 are the offset into the symbol table to go and find the string. Well, this is 0. It's only true if it's not 0, so that's not what this is. Rats. Okay, here's some information, some more information, and then we have this guy. This is in Little Endian, so it's 0, 1. And what is that? That is the section index, and so this is section 1, which happens to be text. And so when we look at the next one, we expect that to be 2. Let's go look at the next one. So we add 18, and that becomes 70 because it's hex. And sure enough, it's 2, just like we would expect it to be. All right. So that's making some sense. The next one, however, we expect it to actually have some information in there. So let's go ahead and do that. Aha! Look at this. Now, this offset to the symbol is not 0. It's actually 0, 0, 0, 1. Because, again, Little Endian. So it offset 1 into the table, we would find this symbol. Okay. Seems fine. What was that table again? Well, it's the string table. Look in the string table. Begins at 21D8. We're going to go ahead and look 7A bytes into it and print those out. So here it is, and this string occurs at offset 1, begins right here, and it's hello.asm, and sure enough, that's what that entry is. What's the value associated with it? Well, let's see. 1, 2, 3, 4 for the offset. This is info. This is other. These 2 bytes, those are this section header thing. And that's not what this is. This is not a section header. This is the file name, so it gets a weird entry. And then that's followed by 1, 2, 3, 4, 5, 6, 7, 8. This is the value, and the value happens to be all zeros. And sure enough, over here we see all zeros. And then that's followed by 8 bytes of length, which is all zeros, and that's what we see here. So, not super interesting. Let's go on to the next one, which will be this guy. And it should tell us, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. The offset in hex should be B. Let's go see what it is. Let's go with the right window. And let's add 18 to this address. And that would be a 0. There it is. And so the first 4 make up the offset, a Little Endian 0, 0, 0, 0, 0, 0, 0, B, which is exactly what we expect. It's pointing right here. Great. So then we have the info byte, the other byte, and then we have the section that it's in, and it's in the text section. It's in section 1. We've agreed that that's text, and sure enough, that's where it is. Great. Then we have 1, 2, 3, 4, 5, 6, 7, 8 bytes over here that give us the value. And the value looks like 00000000401030. And right there it is. That's the virtual address of this target in my program. And then the length is 0. Length of all these things happens to be 0. And we could walk on like this through it. So, symbolic names that or just, in this case, character strings that represent values. And that's it. And the string table holds the bytes that make up the string. The symbol table tells you how to map a pointer to a string to an actual value, which might be an address or it might just be a value or something else. And that's how that works.